Today we're going to talk about word vectorization. I'm going to try to talk to you about this as simplistically as I can. I'm a big fan of the Albert Einstein method of teaching, which is that if you can't explain it to a kindergartner, then you don't actually understand it. And I see a lot of people overcomplicating the concept of vectors because I think a lot of people don't understand it. Vectors is very simplistic once you understand it. We're all familiar with vectors. You were taught vectors in first grade, I guarantee it. So the very first concept that we're looking at here is a concept of 2D vectors, right? This is a visualization of 2D vectors. And then so everyone should be familiar with this, right? This is just a simple graph chart and plotting on a simple 2D graph, right? And then we have positive and negative numbers on this graph. And then so you can go and you can have real or like vectors. It doesn't matter if the numbers are real or not. That's number one, right? Like it's just the number. It's just numbers. So like vectors, it's any number, real or imaginary, positive or negative. And then in a 2D plane, very straightforward, very simplistic. In the 3D plane, it's also simplistic. I think most people are very familiar and have seen something like this visualization, right? And this would be a visualization of a 3D vector. And then so we're super familiar with 2D vectors and 3D vectors. What most people might not understand and might not know is that vectors go beyond that. So they go like, there's a difference between real vectors and mathematical vectors. And then so in real terms, vectors go up to 7 dimensions. You can, like, it doesn't look good, but you could go and you could create a 4-dimensional visualization, 5-dimensional, 6-dimensional, 7-dimensional, etc. Right? But mathematically speaking, there's no limit to this, meaning that if I plot 1,000,000 dimensions, it works mathematically. I can do the math on it mathematically, and I can do all of the same mathematical functions and equations on 1,000,000 dimensions of vectors that I can with 3 dimensions of vectors. And this comes into play when you look at these like levers, right? And then so the next concept and the next important thing to break down within this is that so this and this, these charts that we're looking at here, these are visualizations of the concepts, right? When we're talking about vectors in mathematical terms, they look exactly like this, like little tables, right? And then so 1-dimensional vector, 2 dimensionals, 3 dimensions, etc. Right? And then so it's just this, and then these tables, they can be represented in mathematical terms vertically or horizontally, right? And then so, but that's literally all a vector is these. And then so, but these are vectors on simple numbers, and then you can have complex numbers as well, which introduce both numbers and letters. It's kind of like the bottom line of complex numbers, but complex numbers allow you to represent literally anything. And then so that's where we get into the real power of vectors, right? Because complex numbers allow us to vectorize anything. We can vectorize words. We can vectorize different types of cookies. See, like, so if we want to, for example, vectorize different types of cookies, this is what the vectorization for cookies would be. And then so in this instance, we have cookies and then our vector for cookies. And then in this instance, it's a 3-dimensional vector. So we would have chocolate chip, oatmeal raisin, and sugar cookie. And these would be dimensions 1, 2, and 3, right? So it would be, let's say, VC1, VC2, and VC3. Vector cookie 1, vector cookie 2, vector cookie 3. And then that's exactly how you would lay it out. And then we could have 20 dimensions of cookies. And then we could have and we could have the cookies, we could have the dimensions, the vector dimensions represent the ingredients of cookies, the flavor of cookie, the texture of cookie. It could represent different categories, right? And we could have different tables of vectors, different categories of vectors, and they could all work together. And then that's where you start getting into like kind of these understanding how these vectors can operate like levers that you can pull when you're getting a whole bunch of them together, right? And then so when we talk about vectorizing words and sentences, it's the same type of concept. So if I have a sentence like I love cookies, I can utilize word vectorization and different methods of word vectorization to turn the letters of I love cookies and the words into numbers. And then these numbers become literal vectors, and then they become essentially like this, are letterized, and then are literally you could plot them out on a 2D graph or a 3D graph, right, and visualize them on a multidimensional graph and actually visualize them out. And when you go through, that's actually what you're getting down to and what you're talking about and boiling these things down to. And then so when it comes down to like the problems with word vectorization and things like that, right, it all comes down to the number of these dimensions that you break down these words to. So like the big concept is that if I have 3 dimensions, and so if I have our 3-dimensional example here, as opposed to a 300-dimensional example, this is a lot easier to compute than our 300-dimensional example, right? Our 300-dimensional example, you would imagine, starts to get more mathematically complex, then harder for the machine. And then if it's 3,000, same thing, 3 million, 3 billion, 3 trillion, right? And then when we start getting into numbers like that, and these numbers can explode very quickly because you're multiplying these together, right? So then let's say that we have vectors for cookies, and then we have our types of cookies. So we have chocolate chip, oatmeal raisin, and then sugar cookie. But then let's say that we have another vector category of like ingredients. So we have like sugar, butter, milk, flour, and then we combine, and we in instances where we would need to, we would multiply our ingredients table times our finished cookie table, and then in that instance we get a plethora, like a explosion of additional combinations, right? Because in that instance we're multiplying. This is a good example, right? Because we'd be multiplying, like, say, like 3 dimensions of finished cookie times like 5 dimensions of ingredients. And then so in that instance, you'll notice one thing, right? These aren't the same shape. So the very first thing that we need to do is restructure the tables so that they're the same shape. When we're multiplying the tables against each other, we always want them to be the same shape. So that would be step 1. So we would restructure our cookie table to be 5 dimensions, or we would restructure our ingredient table to be 3 dimensions, and they would be the same. And that includes, and that's involving math that is complexity onto the system in and of itself, right? And then you have all of those dimensions that have to be multiplied, and then it's if you do like 5 times 5, that's a lot, right? 3 times 3 is a lot there as well. And then you have like if you do like 3 times 3, then it's 9 combinations. If you do 5 times 5, it's 25 combinations. Like you're getting like higher and higher with the complexity. Like easily with that type of math, you can see how it just easily explodes, right? It's exponential with those exploding gradients. And then there's some things that you can do to shave that, but then when you start shaving off those exploding gradients and you start shaving that, you're shaving accuracy. You're sacrificing accuracy is all that you're doing, right? So then your knife that you're cutting, like you don't want to be cutting. And then so that's kind of your tool, right? You have levers with the dimensions, and then a knife to cut down the dimensions to save compute. And then that's all that vectors are, all that vectorization is at the end of the day. 2D vectors. This is really like what a LLM model is doing, is it's doing this for words, right? But it converts words into tokens, and then it converts vectors. It converts words into vectors, and then vectors into tokens. And then so the model operates off of tokens, which is why you have to create vector stores for everything, right? And then so all you have to do in order to get information to an LLM model is figure out a way to vectorize it. And then so again, breaking down this concept and leaving it here, vectors can represent anything that you want. And then so that's the beauty of this, and that's where the fun of this comes in, right? The addictiveness of getting into ML and like statistics and data science and all of that is all around this, because of the fact that like once you get into kind of the alchemy of it, you realize it's limitless. It's a unlimited universe and a playground in which you can experiment and do anything. And so it's pretty cool to operate within that type of universe. And so hopefully this has been useful for you, and a very simplistic breakdown of vectorization. If you like this type of content, please like and subscribe. Thank you very much.